Tonight, we're going to sit with one of the longest empirical results in modern science. The cosmos has been listened to for 60 years by some of the most sensitive instruments ever built, by some of the most patient observers in human history, and the cosmos has not, in any direction, said a single recognizable word. 60 years is a long time. For most of that time, the silence was treated as expected. Frank Drake pointed a radio telescope at two nearby sun-like stars in 1960, listened for a few months, heard nothing, and the scientific community shrugged. He had only just begun. Two stars are not a representative sample of the cosmos. The silence, in those first months, was a measurement boundary, not a signal in itself. 60 years later, the silence is no longer the boundary of measurement. It is the measurement. We have listened to thousands of stars in dozens of radio bands, with progressively more sensitive instruments, across decades of dedicated programs. We have looked for laser pulses, for unusual infrared emissions, for chemical fingerprints of industry, for anomalous transit signatures, for direct visitations by probes. We have done all of this with the most careful and thorough work that human astronomy has ever managed, and the cosmos has continued to be quiet. The silence is, by every available measure, real. Tonight we're going to walk into what this silence actually means, not the headline version, which has been compressed into clickbait about aliens hiding from us. The careful version, in which we will look at what we have actually searched for, what we have actually found, what hypotheses serious researchers are now considering, and what the silence implies for the question of whether you are alone, in some meaningful sense, in the cosmos around you. Before we get started, sit with the basic shape of this. The silence is not equivalent to absence. It is consistent with many different possibilities. The cosmos could be empty of intelligent life. The cosmos could be full of intelligent life that has chosen not to broadcast. The cosmos could be full of intelligent life that is broadcasting in modes we cannot detect. The cosmos could be full of intelligent life that has been deliberately hidden from us. Each of these possibilities has its own implications for what we should think about our place in the universe. None of them is comfortable. Tonight, we're going to walk through 5 specific truths about the cosmic silence. Each one is the result of careful work. Each one has implications for what the silence means. By the end of tonight, you will have walked slowly through each one with enough detail to feel the weight of what 60 years of empty radio bands actually implies for your particular cosmic moment. The 5 truths are these. The first truth is that the silence is real and complete across every category of signal we have ever searched for. There is no narrowband radio whisper. There is no laser pulse from any of the nearby stars we have monitored. There is no infrared signature of Dyson swarms around any of the candidate stars we have surveyed. There is no anomalous transit pattern consistent with megastructures. There is no probe in our solar system whose origin we can identify as anything other than natural. The silence is not partial. The silence is complete. The second truth is that the silence is not what the standard expectations predicted. Frank Drake, in the 1960s, developed an equation that estimates the number of communicating civilizations in our galaxy. Under reasonable assumptions about each of the parameters, the equation predicted that the galaxy should contain tens of thousands to millions of active civilizations at any given moment. Even with much more conservative assumptions, the equation predicted that we should hear from at least some of them. The actual number we have heard from is 0. The discrepancy between the expectation and the observation is the empirical heart of the Fermi paradox. The third truth is that the silence has multiple competing explanations, and most of them are disquieting. Some researchers think the silence means that intelligent life is much rarer than the Drake equation suggested. Some think the silence means that civilizations end shortly after they begin. Some think the silence means that civilizations deliberately hide from each other. Some think the silence means that civilizations eventually move beyond physical space in ways that make them undetectable. Each of these explanations has serious proponents. Each of them implies something specific about the future of our own civilization. The fourth truth is that the silence is shaping what physics and philosophy now take seriously. The Fermi paradox is not just an astronomical puzzle. It is a framework for thinking about cosmic intelligence that has produced substantial work in cosmology, in evolutionary biology, in game theory, in the philosophy of mind, and in the long-term study of civilizations. The silence has pushed serious researchers to consider hypotheses that would have seemed too speculative a generation ago. The silence has, in this sense, become one of the most productive empirical results of modern science, precisely because of how much it does not tell us. The fifth truth is that the silence is yours. You're part of the first generation in human history that has confirmed it. 60 years of careful listening has not produced a single confirmed signal. Your specific cosmic moment is the moment in which the silence has become a measured feature of the cosmos, rather than a temporary gap in our knowledge. The silence is not just about the cosmos. The silence is about your particular position in it. 5 truths, 5 facets of the same long empirical result. By the end of tonight, you will have walked slowly through each one, with enough perspective to see why this particular silence matters more than the popular discussion usually acknowledges. Pattern interrupt. The tone of this story should not be panic. The silence is what it is. The cosmos is what it is. The careful work of listening is one of the most patient and noble scientific projects humans have ever undertaken, and the work continues regardless of what the results suggest. The point of tonight is to sit with the results gently, to feel their weight without rushing past them, and to think carefully about what they might mean for your particular cosmic existence. Now, let's begin with the first truth. And the first truth requires us to walk through what we have actually searched for over the past 60 years. The first sustained search for extraterrestrial intelligence was Project Ozma, conducted by Frank Drake in April and May of 1960. Drake pointed the 85-foot radio telescope at the Green Bank Observatory in West Virginia at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani. He listened for narrowband radio signals at the 21 centimeter wavelength, the natural emission frequency of neutral hydrogen, on the theory that any technological civilization might choose this frequency for interstellar communication because it is a universal feature of the cosmos. Project Ozma lasted about 4 months. Drake spent 200 hours observing each of his target stars. The result was negative. No signals were detected from either star. The project ended, and Drake returned to other work. The negative result was treated as the natural starting point for a longer program, not as a definitive answer. The longer program began in earnest in the 1970s and 80s. The NASA SETI program, which conducted systematic surveys of nearby stars, ran from 1992 until it was defunded by Congress in 1993 after only a year of operation. The Project Phoenix program, conducted by the privately funded SETI Institute, picked up where NASA had left off and ran for 9 years, from 1995 to 2004. Phoenix surveyed about 800 nearby stars, listening across a wide range of radio frequencies with the most sensitive instruments available at the time. The result was negative. By the end of tonight, you're going to understand that this pattern of careful searches producing negative results has been repeated many times over the past 60 years. The Allen Telescope Array, a dedicated SETI facility in Northern California, has been operating since 2007. The Breakthrough Listen program, funded by Yuri Milner with a $100 million commitment, has been operating since 2016 and has access to multiple major radio observatories around the world. The optical SETI programs, looking for laser pulses, have been running at the Lick Observatory in California and at Harvard since the 1990s. Each of these programs has produced negative results. The cumulative listening time integrated across all the major Ceti programs over the past 60 years, is now measured in millions of hours. The number of stars surveyed is in the thousands. The number of frequency bands probed is in the dozens. The combined sensitivity of the modern programs is many orders of magnitude better than the sensitivity of Project Ozma. The cosmos has been listened to with extraordinary patience and care. The silence is, in this sense, not the result of inattention. It is the result of careful and sustained attention that has, across multiple generations of instruments, found nothing. No one expects, on first encountering the Ceti program, that 60 years of dedicated listening would produce no confirmed signals at all. No one predicts that the cosmos, despite its size and its age, would be quite this quiet. Absolutely no one anticipates the way the silence has become, over 6 decades, one of the most consistent and reproducible empirical results in modern science. Pattern interrupt, there has been one famous exception to the silence. In August of 1977, the Big Ear radio telescope at Ohio State University detected a narrowband signal that lasted for 72 seconds and then disappeared. The signal was so strong and so coincident with the kind of signal SETI was designed to detect that the astronomer reviewing the data, Jerry Eman, wrote the word "wow" next to the printout. The signal has become known as the wow signal. It has never been detected again, despite many subsequent attempts to revisit the same patch of sky and listen for a recurrence. The wow signal is, in some sense, the most tantalizing single result in the history of SETI. It looks like the kind of signal that SETI was set up to find. It came from a particular direction. It had the right frequency characteristics. It lasted long enough to be measured carefully, but it never repeated. Without a second detection, the signal cannot be confirmed as extraterrestrial in origin. It might have been a one-time astrophysical event. It might have been a brief technological signal from a civilization that no longer broadcasts. It might have been an artifact in the data that we have not yet identified. The wow signal remains, as of this moment, the only signal in the history of SETI that even comes close to looking like a positive result, and it remains officially unexplained. Tonight, we're going to spend a longer pass on the specific history of the SETI program, because the institutional history is one of the more remarkable scientific stories of the past 60 years, and is worth telling carefully. Frank Drake was a young radio astronomer at the National Radio Astronomy Observatory in Greenbank, West Virginia, when he conceived Project Ozma in 1959. Drake had been thinking about the possibility of detecting radio signals from civilizations on other stars. He proposed using the 85-foot Tittel telescope at Green Bank to listen for narrowband signals at the 21-centimeter wavelength, the hydrogen line, on the theory that any civilization interested in interstellar communication might choose this frequency because of its astrophysical significance. The project began in April of 1960. Drake worked alone, with minimal institutional support. He listened to Tau Ceti and Epsilon Eridani for approximately 200 hours each, scanning across a range of frequencies near the hydrogen line. The data was recorded on chart paper and analysed by hand. The instrumentation was, by modern standards, crude. The total bandwidth of the receiver was about 100 Hz, allowing only a single narrow frequency to be examined at a time. Project Ozma ended in May of 1960 after 4 months of observation. No signals were detected. Drake reported the result and moved on to other projects. The initial reaction within the astronomical community was mixed. Some considered the project a serious and important first step in a long-term scientific program. Others considered it speculative and not worth significant investment of resources. Pattern interrupt. The Soviet Union began parallel work in the early 1960s. The Soviet astronomer Iosif Shklovsky, working at the Sternberg Astronomical Institute, became one of the leading theorists of extraterrestrial intelligence. Carl Sagan, working in the United States, collaborated with Shklovsky on a book called Intelligent Life in the Universe, published in 1966. The book became a seminal text in the field and helped to legitimize SETI as a serious area of scientific inquiry. The first major institutional effort came in the early 1970s with the Cyclops project, a study commissioned by NASA. The Cyclops report, published in 1972, proposed the construction of a dedicated SETI facility consisting of roughly 1,000 large radio dishes operating as an integrated array. The Cyclops facility would have been the largest radio telescope ever built, with a total collecting area of several square kilometers and a sensitivity sufficient to detect technological signals from civilizations within a few thousand light-years. The Cyclops proposal was never funded. The cost was prohibitive and the political support was insufficient. But the Cyclops report shaped the subsequent direction of SETI work. It established that systematic, sustained and well-funded searches were technically feasible. It established the engineering specifications for what such searches would require. It established the framework within which subsequent SETI programs would be designed. By the end of tonight, you're going to understand that the next major effort came in the 1980s with the NASA Microwave Observing Project, later renamed the High Resolution Microwave Survey. This was a two-part program. The first part was a targeted search of nearby sun-like stars at high sensitivity. The second part was an all-sky survey at lower sensitivity. The program began in 1992 and was funded for approximately 1 year before being cancelled by Congress in 1993. The cancellation was driven by political opposition to government funding of Ceti, despite the relatively small budget involved. The cancellation could have ended the SETI program. Instead, the private SETI Institute, established in 1984 in Mountain View, California, picked up the work. The institute, funded by private donations, continued the targeted search component of the cancelled NASA program under the name Project Phoenix. Phoenix ran from 1995 to 2004, surveying approximately 800 nearby sun-like stars using time on multiple major radio observatories around the world. The third generation of SETI began in the early 2000s with the construction of dedicated facilities. The Allen Telescope Array, located at Hat Creek in Northern California, was the first major radio telescope built specifically for SETI work. The array was conceived as a collaboration between the SETI Institute and the University of California, Berkeley, with funding from Paul Allen, the co-founder of Microsoft. The initial design called for 350 antennas, though the realized array consists of 42 antennas due to budget constraints. The Allen Telescope Array began full operation in 2007 and has been conducting SETI surveys continuously since then. The most recent major development was the Breakthrough Listen program, announced in 2015 by the billionaire investor Yuri Milner. Milner committed $100 million over 10 years to fund SETI research at unprecedented scale. The Breakthrough Listen program has access to time on the Greenbank Telescope in West Virginia, the Parkes Telescope in Australia, the automated Planet Finder optical telescope at Lick Observatory, and various other instruments. The program is, by any reasonable measure, the largest and best-funded SETI effort in history. No one expects, on first encountering the SETI program, that it would have such a complex institutional history, with periods of public enthusiasm followed by periods of defunding, followed by private rescue and renewed support. No one predicts that the field would survive the various political and budgetary challenges it has faced over 6 decades. Absolutely no one anticipates the way the SETI program has, through the persistent work of multiple generations of researchers, continued to expand its empirical reach, despite the consistent negative results. Hold this image. 60 years of work, 3 generations of instruments, multiple major programs, periods of public support and periods of public skepticism. Private foundations stepping in when government funding lapsed. The continued patience of the research community in the face of consistent negative results. The SETI program is one of the more remarkable institutional achievements in modern science, even if the empirical results have been disappointing. By the end of tonight, you're going to understand that this institutional history is part of what gives weight to the current state of the silence. The silence is not the result of a brief or casual investigation. It is the result of a sustained and well-resourced program that has, across 6 decades, accumulated extraordinary amounts of data and has consistently failed to detect any positive signal. The institutional persistence is itself an empirical contribution. The silence has, in this sense, been earned through careful and patient work. By the end of tonight, you're going to understand that the wow signal is the closest thing the silence has offered to a break in the pattern. Even with the wow signal, the silence is still, by every reasonable measure, complete. 60 years of listening has produced one suggestive event that we cannot confirm, and tens of thousands of hours of negative results that we can confirm. The silence is the consistent feature. The wow signal is the exception that has not become a rule. The second truth is that the silence is not what the standard expectations predicted. The Drake equation, formulated by Frank Drake in 1961 at a meeting at the Green Bank Observatory, was the first serious attempt to estimate the number of communicating civilizations in the galaxy. It has, in the 6 decades since, become the standard framework for thinking about cosmic intelligence. Tonight, we're going to walk into the equation slowly, because understanding what it predicts and why the predictions do not match the observed silence is one of the most important steps in feeling the weight of the Fermi paradox. The equation is simple in form. It multiplies together 7 factors, each of which represents a step in the chain from cosmic conditions to active communicating civilizations. The first factor is the rate at which stars form in the galaxy. The second is the fraction of those stars that have planets. The third is the average number of habitable planets per planetary system. The fourth is the fraction of habitable planets where life actually arises. The fifth is the fraction of those where intelligence evolves. The sixth is the fraction of intelligent species that develop communication technology. The seventh is the average lifetime of a communicating civilization. By the end of tonight, you're going to understand that each of these factors has its own degree of empirical support. The early factors dealing with stars and planets have become much better constrained over the past 60 years. The later factors, dealing with biology and civilization, remain almost entirely unknown. The star formation rate is well measured. The Milky Way produces, on average, 1 to 3 solar masses of new stars per year, integrated across its disk. The fraction of stars with planets is now known to be high, from the Kepler and TESS exoplanet surveys. More than half of all stars have at least one planet, and many have several. The fraction of stars with planets in the habitable zone is estimated at perhaps 10 to 20%, based on the same surveys. The fraction of habitable zone planets that are actually habitable, in the strict sense of being able to support liquid water on the surface, is harder to estimate, but is probably in the range of 1 to 10%. Many habitable zone planets orbit stars whose activity makes long-term habitability difficult. Many are tidally locked, with one side permanently facing their star. Many lack the magnetic fields or atmospheric inventories needed to maintain stable climates. The actual fraction of viable habitable worlds is therefore smaller than the simple habitable zone count. Pattern interrupt. The latter factors of the Drake equation are where the genuine uncertainty lies. We do not know how often life arises on habitable worlds. The honest answer is somewhere between 0.1% and 100%, with vast uncertainty in between. We do not know how often intelligence evolves once life exists. We do not know how often technological civilization emerges from intelligence. We do not know how long technological civilizations typically last. Under reasonable assumptions for each of these factors, the Drake equation produces a wide range of predictions. Frank Drake's own original estimate in 1961 was that the galaxy should contain about 10,000 communicating civilizations at any given moment. Carl Sagan, in his subsequent work, sometimes estimated even higher, with as many as 1 million civilizations. even with conservative assumptions where life is relatively rare and civilizations relatively short-lived, the equation predicts at least dozens of civilizations. The observed number, after 60 years of careful listening, is 0. The discrepancy between any reasonable Drake equation estimate and the observed silence is large. This is the empirical heart of the Fermi paradox. The cosmos, by the standard expectations, should be loud. The cosmos is quiet. Something in the chain from cosmic conditions to detectable civilizations is producing fewer civilizations than the simple counting predicted, or producing civilizations that are not detectable for some reason, or producing them at times when we are not listening, or in places where we cannot see them. The cosmic silence is therefore not just an absence of signal. It is empirical evidence about the parameters of the Drake equation. Walk with me through the most influential recent work on this question. In 2018, 3 researchers at the Future of Humanity Institute in Oxford, Anders Sandberg, Eric Drexler, and Toby Ord, published a paper titled Dissolving the Fermi Paradox. They argued that the standard estimates of the Drake equation parameters had failed to properly account for the wide uncertainties involved. When they did the calculation more carefully, treating each parameter as a probability distribution rather than a single number, they found that the cosmos plausibly contains either no other civilizations at all, or vastly many, with the most likely outcome being that we are essentially alone in the observable universe. By the end of tonight, you're going to understand that the Sandberg-Drexler-Ord analysis is one of the most carefully done treatments of the Drake equation in its history. They did not argue that civilizations definitely do not exist. They argued that the wide uncertainty in the parameters means that the question of whether other civilizations exist is, in some sense, ambiguous from the inside. The simplest extrapolation gives a low probability of other civilizations being detectable from our position. The work has been influential in shifting the discussion of the Fermi paradox in serious circles toward more careful uncertainty quantification. Before we get started, sit with what follows. The implication of the Sandberg-Drexler-Ord work is that the silence may not be a deep mystery. It may simply be that the underlying parameters of the Drake equation push the typical outcome toward us being alone. The cosmos may be quiet because cosmic conditions are not as conducive to the production of detectable civilizations as the optimistic estimates suggested. No one expects, on first encountering the Drake equation, that the careful treatment of the uncertainties would push the typical estimate toward us being alone. No one predicts that the most influential recent analysis would suggest the silence is not a paradox at all, but a natural consequence of the parameter uncertainties. Absolutely no one anticipates the way the conversation about cosmic intelligence has shifted over the past decade toward more careful uncertainty handling. But not everyone accepts this conclusion. Other researchers continue to argue that the silence does require explanation beyond simple parameter uncertainty. Their position is that even with conservative parameter choices, the expected number of civilizations across the history of the cosmos is large. The silence, therefore, requires some specific mechanism that suppresses the number of detectable civilizations beyond what the simple Drake calculation predicts. The various hypotheses we'll walk through in the next truth all attempt to provide such mechanisms. Hold this thought. The Drake equation is the standard framework for predicting cosmic intelligence. The standard predictions under reasonable parameter choices suggest that we should see civilizations. The observed silence implies that something is reducing the actual count below the predicted count. Whether the reduction is due to parameter uncertainty, as the Sandberg-Drexler-Ord analysis suggests, or due to a specific mechanism, as other researchers argue, is part of the active debate in the field. By the end of tonight, you're going to understand that this is a remarkable empirical result in its own right. The cosmic silence, considered as a constraint on the Drake equation parameters, tells us something specific. Either life is much rarer than the optimistic estimates allowed, or intelligence is much rarer, or civilizations are much shorter lived, or some specific mechanism is hiding the civilizations from our detection. Each possibility implies something about the broader structure of cosmic life and intelligence. Before we walk into the third truth, take a slow breath here. The story is about to take a brief turn into a different kind of conversation. We should pause to acknowledge why this kind of careful walk through the silence exists at all. Tonight, we're going to spend a longer pass on the most famous unexplained event in the history of Ceti, because the wow signal deserves to be understood in some detail, and because the surrounding history illustrates much of what is hard about the search. The signal was detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University. The Big Ear was a fixed-orientation radio telescope built in the early 1960s with a beam that swept across the sky as the Earth rotated. The telescope was operated by John Krause and his team as part of a general SETI survey called the Ohio Sky Survey. The survey had been running for years, recording observations on chart paper and reviewing them manually for any anomalous signals. On the night in question, the chart paper showed a signal that lasted for 72 seconds and was, by every measurable property, exactly the kind of signal SETI had been designed to detect. The signal was narrow-band, meaning it occupied only a very small range of frequencies. It was strong enough to substantially exceed the background noise. Its frequency was near the hydrogen line, the same frequency Frank Drake had used in Project Ozma 17 years earlier. The rise and fall pattern of the signal was consistent with the sweep of the telescope beam across a fixed source in the sky. Jerry Amon, the volunteer astronomer reviewing the chart paper several days later, noticed the signal. He circled it with a red pen and wrote the word "wow" in the margin. The signal has become known, in the half-century since, as the wow signal. It remains the single most tantalizing event in the entire history of Ceti. By the end of tonight, you're going to understand that the wow signal has been investigated extensively in the years since. The Big Ear telescope continued to monitor the same patch of sky for years afterward, hoping to detect a recurrence. None was found. After the Big Ear was decommissioned, other telescopes, including the Very Large Array and the Allen Telescope Array, conducted follow-up observations of the same direction. No additional signals were detected. Pattern interrupt. Several proposed explanations of the wow signal have been advanced over the years. The most carefully developed natural explanation was proposed in 2017 by Antonio Paris, who suggested that the signal might have been produced by a passing comet, specifically comet 266P/Christensen, whose orbit took it near the relevant patch of sky in 1977. The hydrogen cloud surrounding the comet, according to this proposal, could have emitted radio waves at approximately the right frequency for a short time. The proposal was investigated, but follow-up work showed that the proposed comet explanation did not quantitatively match the observed signal properties. The hydrogen cloud surrounding a comet would not produce a signal of the observed bandwidth or intensity. The comet proposal has been largely rejected by the SETI community. Other natural explanations have also been proposed. Some have suggested that the signal might have been a reflected signal from a satellite or an aircraft. Others have suggested that it might have been an interference signal from terrestrial radio sources that happened to enter the telescope receiver at the right frequency. None of these explanations has been definitively confirmed. The signal remains officially unexplained. The technological explanation is, of course, that the signal was a real extraterrestrial transmission. The properties of the signal are consistent with what we would expect from a narrowband technological broadcast. The fact that it never repeated could be explained by many factors, including that the source was a short-lived transmission, that the source had moved out of the telescope beam by the time follow-up observations began, or that the source had ceased broadcasting in the interval between the original detection and the follow-up. No one expects, on first hearing about the wow signal, that a single 72-second detection could remain unexplained for almost 50 years. No one predicts that the most tantalizing Ceti result in history would resist definitive interpretation despite repeated follow-up investigations. absolutely no one anticipates the way the wow signal has become a kind of permanent question mark in the empirical record of cosmic listening. The status of the wow signal in the Ceti community is unusual. It is not considered a confirmed positive detection. The lack of repetition makes confirmation impossible. But it is also not considered definitively explained as a natural phenomenon. No natural explanation has been able to account for all of its properties. The signal sits in a kind of permanent epistemic limbo, neither confirmed nor refuted. Now, let's begin to walk through what the modern Breakthrough Listen program has been doing to address the broader question of cosmic silence. The program, funded by Yuri Milner since 2015, represents the largest and most ambitious Ceti effort in history. The total funding commitment is $100 million over 10 years, which dwarfs all previous Ceti budgets combined. The Breakthrough Listen program operates across multiple major observatories. The Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world, has dedicated Ceti observing time. The Parkes Telescope in Australia provides coverage of the southern sky. The Meerkat Array in South Africa, with its 64 antennas, is being used for systematic Ceti surveys. The Automated Planet Finder Optical Telescope at Lick Observatory has been searching for laser pulses from nearby stars. The program is, by every measure, the most comprehensive Ceti search ever conducted. The Breakthrough Listen team has developed sophisticated analysis techniques for processing the enormous data volumes the program generates. The signal detection algorithms can search through billions of frequency channels for narrowband signals, drift signals, and other technological signatures. The analysis pipeline can distinguish between terrestrial radio interference and genuine astronomical signals at increasing levels of confidence. By the end of tonight, you're going to understand that the Breakthrough Listen program, despite its scale and sophistication, has continued to produce negative results. As of the most recent public reports, no confirmed extraterrestrial signals have been detected by the program. Several candidate signals have been investigated and have, in each case, turned out to be either terrestrial interference or natural astrophysical phenomena. The negative results have continued the pattern established by all the previous Ceti programs. The Breakthrough Listen program is committed to running until at least the mid-2020s, with the possibility of extension if Milner's funding continues. The total amount of cosmic listening accomplished by the program will eventually exceed the entire previous history of Ceti combined. Whether the additional listening will produce a positive detection remains to be seen. The pattern of negative results suggests that the silence is, in some real sense, robust against even the most sophisticated and well-funded modern instruments. Hold this image, the wow signal of 1977. 47 years of follow-up investigation, no repetition detected, no definitive natural explanation found. The signal remains the closest thing the silence has offered to a break in the pattern. Around it, the much larger context of Breakthrough Listen and the other modern programs, all continuing to produce the same negative results that have characterized Ceti for 60 years. The silence is, by every available measurement, the dominant empirical feature of cosmic listening. Before we continue, why this channel exists. If you have made it this far into a careful examination of the cosmic silence, you are not the casual viewer the platform expects. You are the person for whom this channel was built. Long-form thinking about cosmic intelligence, at the pace of sleep, with enough technical care to actually feel the weight of the data rather than just the headline summaries, is not what the algorithm rewards. It is what we make anyway, because we believe the deepest questions about cosmic life deserve to be developed slowly rather than collapsed into viral fragments. If that resonates with you, the simplest thing you can do for the channel is to subscribe. Subscribing tells the platform that long, calm, careful work is worth surfacing for the next person who needs a quieter way to think about cosmic intelligence. If you have already subscribed, thank you. Truly. If this is your first long-form night with the channel, welcome. The queue contains many more nights like this one. A small additional note. If Spotify is where you find yourself on sleepless nights, consider following the show there. The audio versions are tuned for the same purpose, the same pace, the same care. We want to be a slow companion across both surfaces. Now, let us return to the silence. The third truth is waiting. The third truth is that the silence has multiple competing explanations, and most of them are disquieting. Tonight, we're going to walk through the 5 leading explanations that serious researchers currently take seriously, because each one has substantial implications and each one paints a different picture of what the silence means for your particular cosmic existence. The first leading explanation is the rare earth hypothesis, developed in detail by Peter Ward and Donald Brownlee at the University of Washington in their 2000 book Rare Earth. The hypothesis argues that the conditions required for complex life to evolve are far more restrictive than the optimistic estimates of the Drake equation allowed. Ward and Brownlee identified a long list of conditions that Earth has happened to meet, including the right type of star, the right orbital distance, the right planetary mass, the right axial tilt, the right rotation rate, the presence of a large moon, the presence of plate tectonics, the presence of a strong magnetic field, the right neighborhood within the galaxy, and many more. Each condition, taken individually, is plausibly common. Taken together, the combination is potentially rare. Quietly, we trace what this implies. If the rare Earth hypothesis is correct, then the cosmos may contain many planets with simple microbial life, but very few planets with a complex multicellular life that could eventually give rise to intelligence. The transition from microbial to complex life in the Earth example took roughly 2 billion years. The transition from complex life to intelligent technological civilization took perhaps another 500 million. Each transition may be substantially rarer than the simple Drake parameters allowed. The cumulative rarity, integrated across all the transitions, could plausibly produce a cosmic count of intelligent civilizations that is consistent with the observed silence. Pattern interrupt. The rare Earth hypothesis is, in some sense, the most reassuring of the 5 explanations. It implies that we have already passed the difficult steps in cosmic biology. The hard work is behind us. The future is, from this perspective, open. If we can avoid destroying ourselves, our civilization may eventually populate the cosmos, because almost no one else will have managed the same difficult journey. The second leading explanation is the Great Filter, articulated most clearly by Robin Hanson in 1998. The Great Filter argues that there must be some specific step in the chain from cosmic conditions to long-lived galactic civilization that is much harder than the others. The step eliminates almost all candidates. The question, for any specific Great Filter argument, is where the filter lies. Is it behind us, in the chemistry of life origins, or in the transition from prokaryotes to eukaryotes, or in the emergence of complex multicellular life? Or is it ahead of us, in the long-term survival of technological civilizations? By the end of tonight, you're going to understand that this question matters enormously. If the filter is behind us, our civilization is among the rare survivors of a difficult selection process, and our long-term prospects are reasonably good. If the filter is ahead of us, our civilization is likely to encounter the same obstacle that eliminated all the prior civilizations that the Drake equation says should have existed. The filter, in this latter version, may take the form of self-destruction through nuclear war, biotechnology, climate disruption, or some other mechanism that we have not yet identified, but that operates with high reliability on civilizations at roughly our current technological level. The most disquieting version of the Great Filter hypothesis is the version in which the filter sits squarely between us and the long-term future. If this version is correct, then almost every civilization that has ever arisen has, at some point similar to where we are now, ended itself or been ended by some process that operates with near universal reliability. We may be the next civilization in this long line. The silence is, in this picture, the cosmic record of all the civilizations that have already ended at this stage. Tonight, we're going to walk carefully through the rare earth hypothesis, because the framework is one of the most detailed and best developed explanations of the cosmic silence and deserves to be understood in its specific content. The rare earth hypothesis was developed by Peter Ward, a paleontologist at the University of Washington, and Donald Brownlee, an astronomer at the same institution, in their 2000 book Rare Earth: Why Complex Life is Uncommon in the Universe. The book argued, in considerable detail, that the conditions required for complex multicellular life to evolve are far more restrictive than the optimistic estimates of the Drake equation allowed. The argument has been refined and extended over the past 2 decades, and the basic framework remains one of the leading candidates for explaining the silence. Ward and Brownlee identified a long list of specific conditions that Earthers happen to meet, and that they argued would be required for any planet to host complex life. The list includes the right type of star, with sufficient brightness to support a habitable zone, but not so much variability that the planet would be sterilized. The right orbital distance from the star, allowing liquid water on the surface. The right planetary mass, sufficient to retain an atmosphere but not so much that the gravity prevents complex organisms from evolving. The right axial tilt, providing seasonal variation but not so much that the climate becomes uninhabitable. The right rotation rate, producing day-night cycles compatible with biological rhythms. Pattern interrupt. The list continues. The presence of a large moon, which stabilizes the planet's axial tilt over geological timescales and provides tidal forces that may have been important for early biology. The presence of plate tectonics, which recycles carbon and other elements between the surface and the interior, regulating long-term climate. The presence of a strong magnetic field protecting the surface from cosmic radiation and stellar wind. The right neighborhood within the galaxy, far enough from the galactic center to avoid frequent supernovae but close enough to have access to heavy elements from previous stellar generations. The right cosmic timing, allowing enough cosmic age for the necessary heavy elements to have been produced. Ward and Brownlee argued that each of these conditions, taken individually, is plausibly common. Many planets in the galaxy might have any single one of these conditions, but the combination, requiring all of them simultaneously, is what makes the configuration rare. The probability of any given planet meeting all the conditions is, in the rare Earth picture, the product of many small probabilities, and the product is potentially very small. Notice that this is the basic logic of the hypothesis. The cosmos may contain many habitable planets, in the sense of supporting simple microbial life. The cosmos may contain very few habitable planets, in the sense of supporting the complex multicellular life that could eventually give rise to intelligence. The transition from microbial to complex life, in the rare Earth picture, requires a set of environmental conditions that is far more restrictive than the conditions required for microbial life alone. The Ward-Brownlee argument has been substantially developed in the years since the original book. Subsequent work has refined some of the specific conditions and added others. The role of long-term climate stability has received particular attention. The role of the early heavy bombardment, which delivered water and other volatiles to early Earth, has been emphasized. The role of the specific composition of the Earth's interior, including the size of the core and the distribution of radioactive elements, has been investigated. Each of these refinements has, in general, strengthened the argument that the Earth configuration is unusual. Walk with me through one specific aspect of the rare Earth argument that has been particularly developed. The role of plate tectonics in regulating long-term climate is now understood to be substantial. Plate tectonics recycles carbon between the surface and the interior through subduction and volcanic outgassing. The recycling process provides a feedback mechanism that stabilizes the long-term climate against the gradual brightening of the sun. Without plate tectonics, the climate of a habitable planet would tend to either freeze or run away into a greenhouse state over geological timescales. Earth has, by every available measurement, the only known active plate tectonic system in the solar system. Mars has had limited tectonic activity in the past, but no longer does. Venus has substantial volcanic activity, but no plate tectonics in the modern sense. The prevalence of plate tectonics on other rocky planets is one of the more important open questions in planetary science. The mechanism that drives plate tectonics is not fully understood. The conditions required for the mechanism to operate are not fully characterized. The fraction of rocky planets in the galaxy that have active plate tectonics is therefore unknown. The rare earth argument suggests that the fraction may be quite small, with most rocky planets either freezing over or running away into greenhouse states because their tectonic systems are not active. No one expects, on first thinking about cosmic biology, that the question of complex life would depend so sensitively on a planetary geological process. No one predicts that the abundance of intelligent civilizations would be substantially controlled by the rarity of active plate tectonics. Absolutely no one anticipates the way the rare earth argument has become a probe of the specific details of planetary geophysics, rather than a general statement about cosmic biology. The rare earth hypothesis has critics. The most common criticism is that the argument is based on a single example, namely Earth, and that drawing general conclusions from a single example is statistically unjustified. The list of conditions Ward and Brownlee identified are, in this critique, simply the conditions that happen to be present on the one planet we know to have complex life. There is no logical guarantee that all of those conditions are actually required. Some of them might be redundant, some might be substitutable by other conditions we have not considered. The list, on this view, overstates the actual restrictiveness of the cosmic conditions for complex life. What surfaces from this is that this critique is, in its way, fair. The rare earth hypothesis is, in the strict empirical sense, a theory based on one data point. The theory may be correct, the theory may be substantially wrong. Until we have additional data, in the form of observations of complex life on other planets, the empirical status of the hypothesis cannot be definitively determined. But the hypothesis is not arbitrary. The conditions Ward and Brownlee identified are in many cases mechanically connected to specific biological or geophysical processes that we understand. The argument that plate tectonics is important for long-term climate stability is not just statistical, it is mechanistic. The argument that a large moon stabilizes axial tilt is not just statistical, it is dynamical. The hypothesis is, in this sense, more than just a list of features. It is a set of testable mechanistic claims that connect specific environmental conditions to specific biological outcomes. Hold this thought. The rare earth hypothesis is the most reassuring of the explanations of the cosmic silence in one specific sense. If correct, it implies that we have already passed the difficult steps in cosmic biology. The future is, on this view, open. The fact that we exist is a sign of extreme cosmic luck, but the luck has already happened. The cosmos may, by every available indication, be largely populated by simple microbial life that has not made the transition to complexity. Our specific cosmic instance is, in this picture, both lucky and valuable. The cosmos is quiet because complex life is rare, not because complex life ends. The third leading explanation is the dark forest hypothesis, popularized by the Chinese science fiction writer Liu Cixin in his novel The Dark Forest. The hypothesis argues that civilizations capable of interstellar communication have, on game-theoretic grounds, strong incentives to remain silent and to destroy any other civilizations they detect. The reasoning is that any civilization could potentially be a threat to any other, and that the technology for cross-cosmic threats develops faster than the technology for cross-cosmic communication. In this picture, the cosmos is full of civilizations that are deliberately silent, watching for any sign of other civilizations and prepared to act decisively against any that reveal themselves. Walk with me through the implications of this hypothesis. If the dark forest is correct, then the silence is not evidence of cosmic emptiness. It is evidence of cosmic caution. Every civilization that survived long enough to be observable would have learned, through bitter experience or through careful game-theoretic analysis, that broadcasting is suicidal. The civilizations that broadcasted were eliminated. The civilizations that learned to stay silent survived. We have not been eliminated because we are too small and too quiet to be noticed. The dark forest is, by far, the most paranoid of the 5 explanations. It is also taken seriously by some game theorists and some thinkers about long-term cosmic strategy. Whether the underlying game theory actually holds up under careful analysis is contested. The hypothesis, as a story, has spread widely in the past decade and has become part of how many people now think about the Fermi paradox. No one expects, on first encountering the cosmic silence, that one of the leading explanations would involve cosmic-scale game theory and deliberate strategic hiding. No one predicts that a science fiction novel from China would have substantial influence on serious discussions of the Fermi paradox. Absolutely no one anticipates the way the dark forest hypothesis has reshaped the conversation about cosmic intelligence over the past decade. Tonight, we're going to spend a careful pass on the dark forest hypothesis, because the framework has become unusually influential over the past decade, and the underlying game theory deserves a proper treatment. The dark forest hypothesis was popularized by the Chinese science fiction author Liu Cixin in his novel The Dark Forest, published in 2008 and translated into English in 2015. The novel is the second book in a trilogy called Remembrance of Earth's Past, which begins with the 3-body problem and concludes with Death's End. The trilogy has become one of the most widely read works of contemporary science fiction in the world, and the dark forest concept from the second book has spread far beyond its original literary context. The basic logic of the dark forest is built on 2 assumptions. The first assumption is that the survival of any civilization is its highest priority. The second assumption is that civilizations cannot easily verify the intentions of other civilizations they detect. Given these 2 assumptions, Liu argues, a third conclusion follows. Any civilization that detects another civilization has a strong incentive to destroy the detected civilization, because the detected civilization might at any future moment develop the capability and the desire to destroy the detecting civilization. The safest course of action is preemptive elimination. What this picture tells us is that this logic, if it is correct, has profound implications for the silence. Civilizations that broadcast their existence would, in the dark forest picture, be detected and eliminated by other civilizations. The civilizations that survive long enough to be observable are precisely the ones that have learned to remain silent. The cosmos is, in this picture, a dark forest in which every civilization is a hunter, hiding carefully and watching for any sign of others, prepared to act with overwhelming force at the slightest indication of another civilization's presence. The implication for our specific situation is uncomfortable. We have been broadcasting radio signals for about 100 years. We have sent deliberate messages, including the Arecibo message in 1974, designed to reach other civilizations. We are, in the dark forest picture, behaving exactly as a civilization that has not yet learned the rules of the cosmic forest. If the picture is correct, our continued broadcasts represent a serious long-term risk. We may have already revealed our position to one or more civilizations that are now considering how to respond. Pattern interrupt. The dark forest hypothesis has been taken seriously by some game theorists and some thinkers about long-term cosmic strategy. The most prominent proponent has been Liu himself, but the underlying logic has been developed independently by various researchers over the past several decades. The hypothesis has implications not just for the cosmic silence, but for active strategic decisions about whether to continue broadcasting, whether to attempt deliberate contact, and how to behave if we ever detect another civilization. The critics of the dark forest hypothesis make several arguments. The first argument is that the game-theoretic logic assumes a particular set of preferences for cosmic civilizations, specifically that survival is the dominant priority. Other priorities, including curiosity, exploration, and the establishment of cosmic relationships, might motivate civilizations to behave differently. The second argument is that the assumption of inability to verify intentions may not hold in all cases. Sufficiently advanced civilizations might develop verification methods that allow them to determine the intentions of other civilizations with reasonable confidence. The third argument is that the cost of inter-civilization warfare may be so high that even rational survival-maximizing civilizations would prefer to coexist rather than to fight. Step back, and you can see that this debate is, in some ways, more nuanced than the popular discussion suggests. The dark forest hypothesis is not a refutation of the possibility of cosmic peace. It is an analysis of the conditions under which cosmic peace might or might not be stable. Whether the underlying assumptions actually hold for any given cosmic civilization is, in the absence of direct evidence about how such civilizations actually behave, an open question. Walk with me through the deeper implications of the dark forest framework. The picture, if correct, has consequences for how we should think about our own civilization's long-term prospects. The most pressing question is whether to continue broadcasting deliberately, given the possible risks. Several prominent thinkers, including the physicist Stephen Hawking and the cosmologist David Brin, have argued publicly that humanity should be cautious about deliberate broadcasting and should consider the possibility that revealing our position could have catastrophic consequences. Others, including Carl Sagan and Frank Drake, argued that the benefits of contact, including the potential transfer of advanced knowledge, outweigh the potential risks. The debate continues. The more philosophical implications of the dark forest are perhaps more interesting. If the cosmos is a dark forest, then the cosmos is structured by fear rather than by curiosity. The dominant force shaping cosmic civilization is, in this picture, the avoidance of detection. The cosmic landscape is one of silent watchers, all of whom have learned that visibility is dangerous. The cosmos, considered as a community of civilizations, is therefore a cold and paranoid place rather than a warm and curious one. No one expects, on first thinking about cosmic intelligence, that one of the leading frameworks for explaining the silence would involve cosmic-scale fear rather than cosmic-scale ignorance. No one predicts that the silence might be the result of strategic choice rather than the absence of communicating civilizations. Absolutely no one anticipates the way the dark forest hypothesis has shifted the conversation about cosmic intelligence over the past decade toward darker and more game-theoretic framings. The empirical status of the dark forest hypothesis is unusual. It cannot be directly tested by ordinary Ceti methods, because the hypothesis predicts that the civilizations themselves would not be detectable. The most that could be done empirically is to detect the consequences of cosmic warfare, such as the destruction of civilizations by other civilizations. Some researchers have looked for evidence of such events in the historical record of stellar phenomena, but no clear evidence has been found. The hypothesis remains, in this sense, theoretical rather than empirical. What this leaves us with is a particular framework that takes the silence seriously and that has gained substantial influence over the past decade. The dark forest hypothesis is not the only explanation of the silence. It is not necessarily the correct explanation, but it is one of the frameworks that thoughtful researchers now consider when thinking about cosmic intelligence, and it has implications that, if correct, would substantially reshape how we think about our own broadcasting and our own long-term prospects. Pattern interrupt. The fourth leading explanation is the transcension hypothesis, developed by John Smart and others over the past 2 decades. The hypothesis argues that civilizations capable of sustained technological development eventually move beyond the constraints of physical space, perhaps by uploading their consciousness into computational substrates that operate at scales much smaller than ordinary planets perhaps by retreating into the interiors of black holes where the laws of physics may permit different kinds of organization, perhaps by transitioning into modes of existence that we cannot currently describe. The implication is that civilizations naturally evolve toward modes of existence that are not detectable by ordinary astronomical observations. We are listening for the wrong kind of signal. We are looking for civilizations that operate at planetary scales and broadcast electromagnetic signals. The civilizations that exist may operate at much smaller scales, or in entirely different physical regimes, where they are essentially invisible to our instruments. The silence is, in this picture, an artifact of our limited search methods. The takeaway is that the transcension hypothesis is, in some sense, the most optimistic of the 5 explanations from a certain angle. It implies that civilizations do not end, they transform. They become something we cannot currently recognize, but that may still be flourishing in modes we have not yet imagined. The silence is, in this picture, a measurement boundary rather than a cosmic absence. The 5th leading explanation is the zoo hypothesis, originally proposed by John Ball at MIT in 1973. The hypothesis argues that the cosmos is, in fact, populated by intelligent civilizations, but that those civilizations have decided to refrain from contacting us. They may be watching, in some passive sense. They may have ethical principles that prevent them from interfering with developing civilizations. They may be running some kind of cosmic observation program in which contact would invalidate the experiment. The zoo hypothesis has, over the decades, been refined into several variants. The quarantine hypothesis suggests that we are deliberately isolated from contact because of some specific concern about our behavior. The interdict hypothesis suggests that cosmic ethics may prohibit contact with civilizations below a certain developmental threshold. The prime directive hypothesis, borrowed from Star Trek, suggests something similar. Each variant has its own implications, but the basic picture is the same. The silence is a feature of choices made by other civilizations, not a feature of their absence. Hold this image: 5 explanations: rare earth, great filter, dark forest, transcension, zoo. Each one is taken seriously by some segment of the research community. Each one has its own implications for what the silence means and what your particular cosmic position implies. The 5 explanations are not mutually exclusive. Several of them could be partially true simultaneously. The combined picture is one in which the silence is in some way expected, but the specific way in which it is expected varies across the 5 frameworks. What this means is that this is part of why the silence is such a productive empirical result. It does not give us a single answer. It gives us a constraint that multiple theoretical frameworks have to satisfy. The frameworks that satisfy the constraint give us different pictures of cosmic intelligence. Whichever framework turns out to be correct, the implications for our place in the cosmos will be substantial. The 4th truth is that the silence has taught us specific things, even in the absence of any positive signal. Tonight, we're going to walk through what 60 years of careful listening has actually contributed to our knowledge, because the contributions are more substantial than the popular framing of negative results usually suggests. The first thing the silence has taught us is the technical capability to actually conduct the search at the precision required. In 1960, when Frank Drake began Project Ozma, the available radio astronomy equipment was orders of magnitude less sensitive than what we have today. The receivers were noisier, the data processing was slower, the frequency coverage was narrower, the sky coverage was limited. The first generation of SETI work was, by modern standards, primitive. The second generation, in the 1980s and 90s, was substantially better. The mega-channel extraterrestrial assay, conducted by NASA's SETI program, used a multi-channel receiver that could simultaneously analyze millions of frequency channels. The Project Phoenix searchers used even more sophisticated multi-channel analyzers. The data processing capabilities improved enormously, allowing the systematic search of much larger frequency and direction grids. The third generation, since 2000 has been transformational. The Allen Telescope Array uses an array of small dishes operating together to provide both sensitivity and field of view coverage. The Breakthrough Listen program uses time on the largest single-dish telescopes in the world, including the Green Bank Telescope and the Parkes Observatory in Australia, plus optical telescopes at the Lick Observatory. The data rates being processed by modern Ceti programs are measured in petabytes per year. The frequency coverage extends from approximately 1 GHz to 10 GHz, with some experiments extending much higher. What this leaves us with is that the modern capabilities are sufficient to detect even relatively modest technological signals from nearby stars. A radio transmitter of the kind used in modern terrestrial broadcasting, if pointed at us from a star within a few hundred light years, would be detectable. A laser pulse of the kind used in modern fiber optic communications, if pointed at us from a star within 1,000 light years, would be detectable. The fact that we have not detected such signals constrains the abundance of such transmitters in our cosmic neighborhood. Pattern interrupt. The second thing the silence has taught us is that the cosmic neighborhood is, with high confidence, not full of broadcasting civilizations. The various Ceti programs have surveyed many of the most promising nearby stars, including all the Sun-like stars within roughly 50 light-years. The negative results from these surveys put quantitative upper limits on the number of civilizations within these distances that broadcast at the frequencies and powers we have searched. The upper limits are tight enough to rule out, with reasonable confidence, the scenario in which the local cosmic neighborhood is populated by easily detectable civilizations. This is a non-trivial empirical constraint. The popular framing of Ceti focuses on the absence of detection. The technical framing focuses on what the absence of detection tells us about the actual cosmic abundance of detectable civilizations. The local abundance is, by the constraints of the search, low. The implications for the global abundance, integrated across the entire cosmos, depend on additional assumptions about how civilizations are distributed across cosmic space. But the local constraint is real and is the most direct empirical result of the Ceti program. The third thing the silence has taught us is about the limits of the standard search assumptions. The early Ceti programs assumed that civilizations would broadcast in particular ways at particular frequencies, on the basis of plausible technological arguments. The silence has, over time, pushed researchers to consider broader and broader categories of possible signal. The optical Ceti programs were added partly because the radio results were consistently negative. The infrared techno-signature searches were added partly to detect possible Dyson swarms or stellar engineering projects. The astronomical anomaly surveys, looking for unusual light curves in stellar populations, were added partly to detect possible megastructures. What becomes clear is that each expansion of the search has been driven by the cumulative weight of negative results in the previous categories. This silence has pushed researchers to be more creative about what they are looking for. The expanded searches have so far also produced negative results. The pattern is consistent. The cosmos has not shown us any obvious technological signatures across any of the categories we have managed to search. The fourth thing the silence has taught us is about the role of physics and engineering in setting natural search priorities. Some categories of signal that would have been considered far-fetched in the 1960s have become standard targets for modern searches. The Breakthrough Listen program, for example, includes systematic searches for what are called narrow-band drift signals that would be consistent with a transmitter on a rotating planet whose Doppler shift varies smoothly with time. The detection algorithms have become extraordinarily sophisticated. The signal characteristics are now treated as engineering specifications rather than just astronomical guesses. The empirical contributions of the silence are also worth recognizing. The various Ceti surveys have, as a byproduct, produced enormous quantities of high-quality radio astronomy data. The data has been used to study natural radio sources, including pulsars, fast radio bursts, and various galactic radio phenomena. The technical instruments developed for SETI have contributed to broader radio astronomy and have informed the design of future facilities like the Square Kilometre Array. The empirical contributions of SETI extend well beyond the search for extraterrestrial intelligence proper. No one expects, on first encountering the SETI program, that the absence of detected signals would produce so much positive empirical knowledge as a byproduct. No one predicts that 60 years of negative results would teach us as much as they have about technology, about the cosmic neighbourhood, and about the limits of our search assumptions. Absolutely no one anticipates the way the silence has become, in a curious sense, one of the most informative empirical results in the history of astronomy. Now, let's begin to think about the fifth thing the silence has taught us, which is perhaps the most subtle. The silence has taught us about the role of patience in scientific work. The SETI program is one of the longest-running coordinated scientific projects in modern history. It has continued through periods of public enthusiasm and periods of public skepticism. It has continued through periods of generous funding and periods of austere defunding. It has continued through generations of researchers who began their careers with one set of expectations and ended them with another. The work has continued because the question is worth asking. The silence is itself part of the answer. Even if we never detect a positive signal, the continued careful work of listening contributes to our understanding of the cosmos. The work is, in this sense, valuable independent of whether it produces a positive detection. The careful patience of the SETI community is one of the more admirable features of modern science. Tonight, we're going to spend a careful pass on one of the more controversial recent developments in the search for cosmic intelligence. The work of Avi Loeb at Harvard University on the possibility that the interstellar object Oumuamua might have been artificial has reshaped the conversation about SETI in important ways and deserves to be examined directly. The story begins in October of 2017, when astronomers using the Pan-STARRS telescope in Hawaii detected an unusual object passing through the inner solar system. The object was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Initial observations showed that the object was moving on a hyperbolic trajectory, meaning that its speed was too high to be bound to the Sun. The object was, in this strict orbital mechanical sense, an interstellar visitor, the first such object ever confirmed. The detailed properties of Oumuamua turned out to be unusual. The object was approximately 100 meters in its longest dimension and only about 30 meters in its shorter dimensions, giving it an extreme cigar shape or possibly a flat disc shape aspect ratio that was unlike any known natural object. The object showed no visible coma or tail, which is unusual for objects passing through the inner solar system at high speeds. The object also showed a small but measurable acceleration that could not be fully explained by gravity alone, suggesting some kind of non-gravitational force was acting on it. What emerges from this is that these unusual properties prompted Avi Loeb to propose, in a series of papers and a book titled Extraterrestrial, published in 2021, that Oumuamua might have been an artificial object of extraterrestrial origin. The proposal was specific. Loeb suggested that Oumuamua might have been a light sail, a thin reflective sheet used by some other civilization for interstellar propulsion that had drifted into the solar system from the interstellar medium. Pattern interrupt. The proposal was controversial. Most astronomers preferred natural explanations for Oumuamua. The leading natural explanation was that the object was a hydrogen iceberg, a relatively rare type of natural object composed primarily of frozen hydrogen, whose sublimation in the inner solar system could explain both the non-gravitational acceleration and the absence of visible coma. Other natural explanations included a nitrogen ice fragment from a Pluto-like body, a disrupted comet, or an unusual carbon-based asteroid. Each of these explanations had its own merits and difficulties. The debate between Loeb and the mainstream of planetary science has been substantive. Loeb has argued that none of the natural explanations adequately accounts for all of Oumuamua's properties simultaneously. The mainstream has argued that the natural explanations, while imperfect, are more parsimonious than invoking extraterrestrial intelligence. Neither side has been able to definitively settle the question, because Oumuamua passed through the solar system too quickly to allow detailed follow-up observations. The object is now far beyond our reach, and the question of its true nature will probably remain unresolved. The point worth taking away is that the Loeb-Oumuamua story has reshaped the broader conversation about Ceti in ways that go beyond the specific case. Loeb has argued more generally that the Ceti community has been too conservative in its consideration of artificial origin hypotheses for anomalous astronomical phenomena. He has argued that the consistent silence of conventional Ceti searches should push researchers to consider broader categories of possible technological signatures, including signatures embedded in objects that pass through the solar system, or signatures that take forms we have not previously anticipated. In 2021, Loeb established the Galileo Project at Harvard, a research program dedicated to the systematic search for evidence of extraterrestrial technological civilizations in astronomical data and in physical objects that may have entered the solar system. The project has been controversial within the broader astronomical community, with some researchers arguing that it represents a productive expansion of the search, and others arguing that it represents a problematic departure from rigorous scientific methodology. The project continues to operate, conducting various surveys and analyses of candidate anomalous phenomena. Walk with me through what the Loeb-Oumuamua story implies for the broader question of the cosmic silence. The conventional Ceti program has focused on signals, particularly radio and optical signals, that civilizations might deliberately broadcast for communication. The Loeb perspective expands this focus to include physical evidence that civilizations might leave in the form of artifacts, structures, or other detectable physical signatures. The expansion is, in some sense, a response to the consistent silence in the conventional searches. If the conventional silence is taken seriously, then perhaps the search should be broadened to other categories of possible evidence. No one expects, on first thinking about cosmic intelligence, that the question of how to search would itself become so contested. No one predicts that a single unusual interstellar object would so substantially reshape the conversation about Ceti methodology. Absolutely no one anticipates the way the Loeb-Oumuamua story has, despite the lack of definitive conclusion, become one of the more influential developments in the field over the past decade. The broader scientific status of the Loeb perspective is mixed. Some researchers have supported the expansion of search methodology, particularly the systematic investigation of anomalous phenomena that might have technological origins. Others have argued that the Loeb approach is too speculative and that the conventional Ceti methodology, despite its consistent negative results, remains the most rigorous available approach. The debate continues, and it is unlikely to be definitively resolved without new empirical data. The Loeb perspective has also influenced public discussion of Ceti in ways that go beyond the academic debate. The popular framing of Oumuamua as a possibly artificial object has resonated with a broader audience interested in extraterrestrial intelligence. The Galileo Project has received substantial media attention. The book Extraterrestrial has been widely read. The broader cultural conversation about cosmic intelligence has, in some sense, been moved by the Loeb work in directions that the more conservative Ceti community might not have chosen. Hold this image. The Loeb-Oumuamua story is one of the more interesting recent developments in the search for cosmic intelligence. It represents a substantial expansion of search methodology, a substantial controversy within the scientific community, and a substantial reshaping of public discussion. Whether the expansion will ultimately produce a positive detection of evidence for extraterrestrial intelligence remains to be seen. The search continues, in both its conventional and its expanded forms. What follows from this is that the Loeb-Oumuamua story is part of why the current moment in Ceti is particularly interesting. The combination of the long silence in conventional searches, the active debate about how to expand the search, and the various influential proposals about what to look for has produced an unusually dynamic period in the field. The next decade will likely see substantial development of new search methodologies, with the question of whether any of them produce positive detections being one of the more consequential open questions in modern astronomy. Hold this thought. The silence has taught us specific things, even in the absence of any positive signal. The technical capability to conduct precision searches, the empirical constraint on the local abundance of broadcasting civilizations, the limits of our standard search assumptions, the role of physics and engineering in setting search priorities, the value of patience in long-term scientific work. Each of these is a real empirical contribution. The silence is not just an absence of result, it is a result with content. Notice that this is, in some sense, the most underappreciated aspect of the cosmic silence. The popular framing treats 60 years of negative results as a failure. The technical framing treats them as a careful empirical investigation that has produced specific knowledge. The technical framing is the more accurate one. The silence is, in its quiet way, one of the most carefully conducted empirical inquiries in the history of science. The work continues, the understanding deepens. The next 60 years will likely produce additional insights, whether or not they produce the positive signal that the program was originally designed to find. The fifth truth is the most personal of all. The silence is yours. You are part of the first generation in human history that has confirmed it. Tonight, we're going to walk into this slowly, because the personal implications of being alive during the empirical confirmation of cosmic silence deserve to be sat with carefully. For all of human history before 1960, the question of whether the cosmos contained other civilizations was a matter of speculation rather than measurement. The ancient Greeks debated it. Medieval theologians considered it. Renaissance astronomers raised it. Enlightenment thinkers explored it. But none of them had instruments that could even begin to test the question empirically. The silence of the cosmos for the entire history of human thought up to the 20th century was either assumed without measurement or denied without measurement. There was no data. Frank Drake's Project Ozma was the first measurement. The negative result was small, in the sense that only 2 stars were surveyed for only a few months. But it was the first empirical contribution to a question that humans had been asking in various forms for thousands of years. The silence began to acquire empirical content with Drake. The content has been accumulating ever since. You're alive at a time when the empirical content has accumulated to the point that the cosmic silence is, in serious scientific circles, treated as a measured feature of the cosmos rather than a temporary absence of data. The careful work of 60 years has produced an answer. The answer is the silence. The silence is, in your lifetime, an established empirical result. What surfaces from this is that what this means for your particular cosmic position. You are not just alive in a cosmos that happens to be quiet. You are alive in a cosmos whose quietness has been carefully documented across multiple generations of instruments, across multiple categories of signal, across multiple major research programs. The quietness is not a guess, it is a finding. Pattern interrupt. Sit with this for a moment. Every human who lived before 1960 could entertain the hypothesis that the cosmos was full of broadcasting civilizations, with the absence of detection being merely a matter of technology. Every human who lives in the present can, if they look at the evidence carefully, see that the technology has been developed and the detection has not happened. The hypothesis of an obviously full cosmos has, in your particular cosmic moment, been substantially undermined by careful work. The cosmos is not obviously full. The cosmos may, by every indication of 60 years of listening, be far quieter than the optimistic hypotheses allowed. This is, in some ways, a profound shift in the human relationship to the cosmos. For most of history, the question of cosmic loneliness was open in the sense that no evidence had been collected. For the past 60 years, evidence has been collected, and the evidence points consistently toward cosmic quietness. Whether the quietness implies actual loneliness, in the sense that other civilizations do not exist, or simply implies cosmic hiding, in the sense that other civilizations exist but are not detectable to us, The answer is the same from our perspective. We do not have neighbours that we can hear. Walk with me through what this implies for your sense of personal cosmic existence. The classical assumption was that humans are part of a cosmic community whose extent we did not yet know. Expectation, classical assumption. Reality, revised assumption based on the careful empirical work of the past 60 years, is that humans are alive in a cosmos that, by every available measurement, is not loud with other civilizations. Whether we are alone in some absolute sense, or whether we are simply alone in some local sense, the practical experience is the same. We do not have signals from other minds in the sky. No one expects, on first thinking about the cosmic silence, that being alive at a particular time would have such a measurable impact on the human relationship to cosmic loneliness. No one predicts that the question of whether we have neighbours would have, in your specific lifetime, accumulated as much empirical content as it has. Absolutely no one anticipates the way the silence has become, over 6 decades, a personal feature of your particular cosmic moment. The implications for how you might think about your own existence are subtle. The classical view was that humans were one community of intelligence among many. The revised view, based on the empirical work, is that humans may be the only community of intelligence within the reach of any signal we have so far been able to send or receive. The two views produce very different pictures of cosmic existence. The classical view places humans in a richly populated cosmic neighbourhood. The revised view places humans in a quiet cosmic neighbourhood, whose quietness has been carefully documented. What this picture tells us is that this revision is not a tragedy. It is an empirical result. The cosmos is what it is. The silence is what it is. Sitting with the silence carefully does not require any particular emotional response. It requires patience. The cosmos has presented us with this particular state of affairs, and our task is to understand it as well as we can. There is a deeper version of this point that connects to the question of human identity in the cosmos. If we are in the practical sense alone in our cosmic neighbourhood, then the value of human consciousness and human civilization may be greater than we would otherwise have estimated. The cosmos has produced this kind of activity, as far as we can tell, in our specific location. The fact that we cannot easily detect it elsewhere may mean that our specific instance is, in some local sense, rare. Rare things are worth taking care of. Mark this moment. The silence is not just about the cosmos. The silence is about you. You are part of the generation that has confirmed it. Your particular cosmic moment, this specific decade, is a moment in human history that no previous generation could have shared. The empirical confirmation of cosmic silence, with all its implications for cosmic loneliness and cosmic value, is something you are alive to witness. The witnessing is not generic. It is specific to your particular cosmic time. Slowly, we sit with what this implies for the way you might experience the night sky outside. The stars, in the classical view, were potentially the homes of distant civilizations. The radio noise that we now know fills the cosmos was, in the classical view, potentially a carrier of distant messages. The space between us and the nearest stars, in the classical view, was potentially a busy highway of cosmic communication. The revised view is somewhat different. The stars are the homes of stars. The radio noise is the radio noise of natural astrophysical sources. The space between us and the nearest stars is quiet. In every direction we have managed to listen. This is not a small revision. It is a substantial reshaping of the cosmos that you live in. The cosmos you live in, on the basis of the past 60 years of careful work, is quieter than the cosmos that classical assumptions described. You are alive at the moment in human history when this revision has become empirical fact. What this leaves us with is a picture of personal cosmic existence that is, in some sense, more solitary than the classical version. You're not surrounded by the kind of cosmic neighbourhood that earlier generations could imagine. You're surrounded by a cosmic neighbourhood that has, by every available measurement, been quiet for as long as we have been able to listen. The solitude is real. The solitude is yours. The solitude is part of what makes your particular cosmic moment unique in the history of human awareness. Tonight, we're going to spend a careful pass on what the cosmic silence implies for the way you might think about your own existence, because the personal implications of being alive in a measured cosmic silence deserve to be sat with carefully. Before we get started, sit with the basic situation. You're reading these words in a particular body, in a particular room, on a particular night, on a planet that has been, by every available measurement of the past 60 years, alone in its cosmic neighborhood. The aloneness may not be absolute. There may be civilizations elsewhere that we cannot detect. There may be civilizations that have deliberately hidden from us. But the practical experience from your perspective is the same as if we were alone in some absolute sense. We do not have neighbors that we can hear. The first practical question is whether this changes how you should think about your own consciousness. The classical assumption was that human consciousness is one example of a broader cosmic phenomenon, with other forms of consciousness presumably existing on other planets. The revised assumption, based on the empirical work, is that human consciousness may be substantially rarer than the classical assumption allowed. Whether we are the only conscious beings in the local cosmic neighborhood, or whether there are others who are simply silent, the practical implication is the same. We are, in our specific cosmic position, an isolated instance of consciousness. No one expects, on first thinking about this, that the cosmic silence would have direct implications for how to value human consciousness. No one predicts that the empirical absence of cosmic neighbors would translate into philosophical implications for the meaning of human awareness. Absolutely no one anticipates the way the silence becomes, in this respect, a kind of cosmic argument for the value of what we have. Mark this moment. The reasoning is straightforward. Rare things tend to be more valuable than common things. If consciousness is common throughout the cosmos, then any particular instance of consciousness is just one of many. If consciousness is rare, then any particular instance of consciousness is part of a small population that, by virtue of its rarity, may be more worth protecting and cultivating. The cosmic silence, considered as evidence that consciousness may be rarer than we thought, has implications for the value we attach to our own consciousness and to the consciousness of others on this planet. The second practical question is whether the silence changes how you should think about humanity's long-term prospects. The classical view was that humanity was one civilization among many, with our specific trajectory being just one example of how civilizations might develop. The revised view, based on the silence, is somewhat different. If most civilizations end before they become observable, as some of the proposed explanations suggest, then our specific trajectory is, in some sense, one of the rare successful ones to date. Our continued survival is therefore both unusual and, if the relevant explanations are correct, requires active maintenance against the various processes that seem to eliminate other civilizations. Step back, and you can see that this has practical implications for how you might think about contemporary risks. The risks of nuclear war, of pandemic disease, of climate change, of unaligned artificial intelligence, of various other potential catastrophes, take on additional weight in light of the cosmic silence. If civilizations consistently fail to navigate these or similar transitions, then our specific transition may be more important than the transitions of more populated cosmic neighborhoods would be. The stakes are higher. The need for careful work is greater. Expectation. The cosmic silence has nothing to do with how we should think about contemporary risks. Reality. The cosmic silence may be one of the strongest pieces of empirical evidence for the seriousness of the risks that contemporary civilization faces, by suggesting that other civilizations have not managed to survive the analogous transitions. The third practical question is whether the silence changes how you should think about the value of cosmic exploration. The classical view was that cosmic exploration would eventually allow us to meet our cosmic neighbors and to participate in a broader cosmic community. The revised view, based on the silence, is more cautious. There may not be neighbors to meet. the exploration may not lead to the kinds of contact the classical view anticipated. The value of cosmic exploration in this picture is not primarily about contact. It is about understanding the cosmos as it is, including its quietness. Now let's begin to consider what this implies for your sense of being alive in this particular cosmic moment. The classical sense of cosmic existence was, in some way, social. You were one consciousness among many across the cosmos. The cosmic community, even if you could not interact with it, was part of the background against which your existence was understood. The revised sense is more solitary. You are, by every available measurement, alone in your cosmic neighborhood. The cosmic community, if it exists at all, is not part of the practical background of your existence. The solitary cosmic existence is not necessarily worse than the social cosmic existence. It is different. It has its own kinds of meaning. The cosmos that has produced a single instance of consciousness in your specific cosmic neighborhood has, in some sense, given that consciousness particular significance. The neighborhood is not crowded. The consciousness is not generic. The specific value of being conscious in a quiet cosmos may, on reflection, be greater than the specific value of being conscious in a loud one. No one predicts, on first encountering the cosmic silence, that the implications might include a kind of cosmic dignity for solitary consciousness. No one expects that the absence of cosmic neighbors might translate into philosophical implications for the meaning of human awareness. Absolutely no one anticipates the way the silence, taken seriously, becomes a particular kind of cosmic context for what it means to be conscious in this specific place and at this specific time. Hold this thought. The cosmic silence has been confirmed across 60 years of careful work. The silence implies that you are, by every available measurement, alone in your cosmic neighborhood. The aloneness has consequences. Some of the consequences are difficult, some of them are interesting. All of them follow from the careful empirical work of the past 6 decades. The cosmos that you live in is, in this sense, particular. Your specific position within it is also particular. The takeaway is that the cosmic silence is not just an astronomical result. It is a feature of how you might think about your own existence, your own civilization, your own consciousness, and your own cosmic position. The silence is, in this respect, one of the most personal empirical findings in modern science. It has implications that extend well beyond the specific question of whether Ceti has detected anything. It shapes the broader context within which contemporary human existence takes place. Tonight, we're going to walk through 5 common misconceptions about the cosmic silence directly, because each one is widely repeated in popular discussion, and each one deserves a clear correction. Now let's begin with the first misconception. The misconception is that the silence proves there are no other civilizations. This is the most common interpretation in popular discussion, and it is technically an overstatement of what the empirical work has actually established. The silence is consistent with several different possibilities, only one of which is that we are alone. The silence is also consistent with civilizations existing but being deliberately silent, with civilizations existing but broadcasting in modes we cannot detect, with civilizations existing but at distances or times outside the reach of our current instruments. The silence rules out one specific scenario, in which the cosmos is loud with broadcasting civilizations at frequencies and powers we have been searching. It does not rule out all scenarios in which civilizations exist. No one expects, on first hearing the popular claim, that the empirical situation could be quite this much more nuanced than the headline suggests. No one predicts that the most widely repeated interpretation of Ceti results would so substantially overstate what the data actually shows. Absolutely no one anticipates the way the gap between the popular and technical readings of the cosmic silence has become a substantial source of confusion. The second misconception is that the silence proves the Drake equation is wrong. The Drake equation is not, strictly speaking, falsifiable by Ceti results. because the equation contains parameters whose values are not independently known. The equation predicts a range of possible civilization counts depending on the parameter choices. The silence constrains the parameter space, ruling out some parameter combinations and leaving others viable. The equation is not refuted by the silence. It is constrained by the silence in specific ways. What this means is that this is a subtle point. The popular framing often treats the Drake equation as a single prediction that has been refuted by the absence of detection. The technical framing treats the equation as a framework that has been constrained by the absence of detection. The framework continues to be useful for thinking about cosmic intelligence. It just produces different specific estimates than it did before the silence had been measured. The third misconception is that the silence means SETI has failed. This claim has appeared in various forms, often with suggestions that the program should be discontinued because of the long history of negative results. The technical reality is that SETI has not failed. SETI has produced an empirical constraint on the cosmic abundance of detectable civilizations. The constraint is, in itself, a result. The result is consistent with the program working correctly. The program has done what it was designed to do, which is to search for signals and to report what it finds. The fact that it has not found signals is an empirical result, not a failure of the program. Expectation. SETI is a failed program because it has not produced positive detections. Reality. SETI is a successful program in the sense that it has produced rigorous empirical constraints on a question that humans have been asking for thousands of years. The constraints are negative, but they are real, and they have substantial implications for how we think about cosmic intelligence. The fourth misconception is that the silence is a recent development. This claim sometimes appears in discussions that frame the silence as a new and surprising result that has emerged only in the past few years. The technical reality is that the silence has been the consistent empirical result of SETI for 60 years. It is not a new finding. It is the longest-running empirical result in the field. Frank Drake's negative result from Project Ozma in 1960 established the basic pattern. Every subsequent program has confirmed the pattern. The silence is, by every measure, an old result that has been steadily reinforced over 6 decades. No one predicts, on first thinking about SETI, that the cosmic silence would have been such a stable empirical result over such a long period. No one expects that the consistency of the negative results would be quite this robust across multiple generations of instruments and multiple major programs. Absolutely no one anticipates the way the silence has become, over decades, one of the most reproducible empirical findings in modern science. Soft pause. The fifth misconception is that the silence means we should give up searching. This claim sometimes appears in discussions about future funding for SETI, with arguments that the consistent negative results suggest the program is not worth continuing. The technical reality is more nuanced. The negative results have constrained the parameter space, but they have not exhausted the search space. There are still substantial regions of frequency, signal type, and search methodology that have not been thoroughly explored. The next generation of instruments, including the Square Kilometre Array and various other planned facilities, will substantially expand the search. Giving up now would mean foreclosing on parts of the search space that have not yet been examined. What this leaves us with is that this is part of why the SETI community has continued to argue for the value of ongoing search work despite the consistent negative results. The search is not exhausted. The empirical question is not closed. Future instruments may produce different results than past instruments have. The reasonable scientific approach is to continue the work, with realistic expectations and with full acknowledgement that the silence may continue indefinitely. Hold this image. 5 misconceptions, each one widely circulated, each one wrong in specific ways. The corrections do not diminish the significance of the cosmic silence. The silence is genuinely significant. The silence has substantial implications for how we think about cosmic intelligence. But the silence is not what the popular framings often suggest. The technical understanding is more measured and, in its own way, more interesting than the popular versions allow. What this leaves us with is a clearer view of what the silence actually means and what it does not mean. The silence is a constraint, not a refutation. The silence is consistent with multiple explanations, not all of which involve cosmic emptiness. The silence is the result of careful and sustained empirical work, not of inattention. The silence has implications for the future of the SETI program, but the implications are not that the program should be discontinued. The silence is, in this sense, one of the more carefully developed empirical results in modern astronomy, and it deserves to be understood in its specific technical content rather than in the popular caricatures that dominate much of the public discussion. Tonight, we're going to spend a careful pass on what comes next in the search for cosmic intelligence, because the directions of current and future work are worth knowing. Now, let's begin with the first major development to expect. The Square Kilometre Array, an international radio telescope being constructed in South Africa and Australia, will dramatically expand the capabilities for SETI work. The array will consist of thousands of antennas operating together to provide a total collecting area of approximately 1 square kilometre, hence the name. The sensitivity will be many times greater than any existing radio telescope. The construction has been underway for several years, and the first major science observations are expected to begin in the late 2020s. The Square Kilometre Array will be able to search for technological signals at sensitivities that would have been impossible with previous instruments. The array will be able to detect, in principle, narrowband transmissions from civilizations at distances of thousands of light years. The array will also be able to search across much wider frequency bands than previous instruments, allowing the detection of signals at frequencies that have not been thoroughly explored. The combination of higher sensitivity and broader frequency coverage represents a substantial expansion of the Ceti search capability. What becomes clear is that the Square Kilometre Array is just one of several major facilities that will reshape SETI over the next decade. The Meerkat Array in South Africa, already operating, is being used for systematic SETI surveys as part of the Breakthrough Listen program. The 500-metre aperture spherical telescope in China, called FAST, is the largest single-dish radio telescope in the world and has recently begun SETI observations. The Allen Telescope Array continues to operate, with ongoing upgrades that improve its sensitivity. The combined capabilities of these facilities, plus the planned Square Kilometre Array, represent the largest expansion of SETI search capacity in the program's history. Hold this image. The second major development involves expanded search methodologies. As we discussed in the context of the Loeb work, the conventional SETI approach has been substantially expanded over the past decade to include various techno-signature searches that go beyond the original focus on radio and optical transmissions. The expansion includes searches for Dyson swarms in infrared surveys, searches for megastructures in transit data, searches for anomalous chemical signatures in exoplanet atmospheres, and searches for physical artifacts in solar system data. Each of these expanded search categories has its own technical requirements and its own potential for positive detection. The third major development involves the systematic analysis of exoplanet atmospheres. The James Webb Space Telescope, which we have discussed in other contexts, is providing the first detailed atmospheric measurements of exoplanets in the habitable zones of nearby stars. The measurements include sensitive detection of various chemical species, including some that might be biosignatures or technosignatures. Whether the analyses produce any positive detection of either biological or technological signatures is an open question. The data is being collected. The analyses are ongoing. The results, when they come, will substantially contribute to our understanding of cosmic life and intelligence. What emerges from this is that the fourth major development involves the broader scientific debate about how to interpret negative results. The consistent silence of conventional SETI has prompted increasing discussion among researchers about what the silence implies and how it should shape future search strategy. The discussion includes the various hypotheses we have walked through tonight, plus newer proposals that take the silence as a starting point for theoretical work on cosmic intelligence. The broader theoretical landscape is, in this sense, becoming more diverse and more sophisticated. No one expects, on first thinking about the future of SETI, that the program would have so many active expansions and so much theoretical development, despite the consistent negative results. No one predicts that the field would be entering a particularly active period despite the long history of silence. It quietly surprises everyone the way the cosmic silence has, paradoxically, energized rather than discouraged the broader research community. The fifth major development involves the possibility of positive detection itself. If the cosmos eventually does reveal a signal, the detection will be one of the most significant events in human history. The implications would extend across science, philosophy, religion, and culture. The protocols for handling such a detection have been developed by the SETI community and have been the subject of substantial international discussion. The protocols include procedures for verifying the signal, for announcing the detection, for analyzing the signal contents, and for considering how to respond. The protocols are designed to handle one of the more consequential possible events in human history with appropriate care. Before we get started on what all this implies, take a slow breath here. The next decade of SETI will be substantially more capable than the previous decade. The expansion of search methodology, the new instruments, the systematic exoplanet analyses, the broader theoretical work, and the prepared protocols for handling positive detection all represent substantial progress in the field. Whether any of this progress will produce a positive detection remains to be seen. The cosmic silence may continue. The silence may, alternatively, break. Either outcome will be informative. Hold this image. We are alive at a moment when the search for cosmic intelligence is entering what may be its most capable phase. The instruments are being upgraded. The methodologies are being expanded. The theoretical understanding is being refined. The protocols are being prepared. The work continues, with substantial energy and substantial resources, despite the long history of silence. The next decade will, in this sense, be one of the more interesting periods in the history of the field. The point worth taking away is that this is part of why the current moment in SETI is unusual. The combination of the long historical silence, the substantial expansion of search capability, the active theoretical debate, and the various influential proposals about what to look for has produced a dynamic and productive period in the field. Whether the next decade produces the silence-breaking detection that the program was originally designed to find, or whether it produces additional decades of confirmed silence, the work itself will continue to contribute to our understanding of cosmic intelligence in ways that go beyond any specific detection. What this leaves us with is a sense of why the current moment matters. We're alive during one of the more capable phases of one of the longest-running empirical inquiries in the history of human thought. The work continues, the instruments improve, the questions get sharper, the implications continue to be worked out. The cosmic silence is being measured with increasing precision, and the measurement itself is part of the empirical contribution that future generations will inherit from our current scientific work. For the rest of the night, sit with the silence as it is. 60 years of careful listening, thousands of stars surveyed, millions of hours of integrated observation time, hundreds of researchers across multiple generations of instruments, dozens of major programs across the world, and, at the end of all of this work, one tantalizing 72-second signal in 1977 that has never repeated, and otherwise a complete and consistent silence across every direction we have managed to point a receiver. Picture for a moment what this means. The cosmos we share in its observable form is large enough to contain 100 billion galaxies and perhaps 2 trillion total galaxies in its full unobservable extent. Each galaxy contains on average 100 billion stars. The total stellar count is staggering. The cosmic conditions for habitable planets exist in vast abundance. The chemistry of life is straightforward. The mathematics of intelligence is presumably achievable in many possible substrates. The cosmos is, by every available measure, full of the raw material for life and for intelligence. And the cosmos, by every available measure of our listening, is quiet. The silence is not partial. It is not localized. It is not a feature of one particular region or one particular search. It is the consistent result of 60 years of work across every category of signal that human ingenuity has been able to devise. The silence is, in this sense, one of the most reproducible empirical results in modern science. The cosmos has been quiet wherever we have looked, in whatever way we have looked. Slowly, the camera in your imagination drifts outward. It leaves the room. It rises above the building, above the city, above the planet. It travels outward through the solar system, the galaxy, the local group, the cosmic web of galaxies. At every step, the same silence. No radio whispers, no laser pulses, no infrared signatures of stellar engineering, no probe trajectories, no anomalous transit patterns, just the natural electromagnetic activity of stars and galaxies and dust and gas, with no recognizable technological footprint. The camera continues outward. It passes through the regions where Ceti has not yet reached, in the more distant parts of the galaxy, in the other galaxies of the local group, in the more distant galaxies of the cosmic web. The silence extends, presumably, into these regions as well. The next generation of instruments may push the listening into these further regions. The silence may, when those regions are searched, prove to be just as consistent as it has been in the regions we have already covered. The camera turns around and begins the long drift back, past the cosmic web, past the local group, past the galaxy, past the solar system, past the planet, through the atmosphere, through the city, through the building, into the room, to the foot of the bed. You are still here. The version of you in this room, on this night, in this particular body, is the version that is alive at the moment when the cosmic silence has become an empirical fact. The cosmos is the cosmos. The silence is the silence. The implications are what they are. What this means for how you experience the night sky outside is subtle. The stars are still there. The galaxies are still there. The cosmos is still beautiful and vast. The view, in the most literal sense, is unchanged. What has changed is the meaning of the view. The cosmos you're looking at, in addition to being the cosmos that contains the stars and the galaxies, is also the cosmos that has been carefully listened to for 60 years and has, by every available measurement, not responded. The cosmos has, in this sense, given you a particular kind of cosmic existence. It is not the cosmos of classical assumption, in which we were one community of intelligence among many. It is the cosmos of empirical reality, in which we are, by every available measurement, alone in our cosmic neighborhood. The aloneness may not be absolute. The aloneness may be local. The aloneness may be due to deliberate hiding by other civilizations. The aloneness may be due to the rarity of intelligence in cosmic conditions. The aloneness may be due to the brevity of technological civilizations. But whatever the underlying cause, the practical experience is the same. We do not have neighbors that we can hear. There is, in this picture, a particular kind of dignity. You're alive in a cosmos whose silence has been carefully documented by some of the most patient scientific work in human history. The work is part of your cosmic inheritance. The silence is part of your cosmic inheritance. The implications for what your existence means in a cosmos whose loudness was once assumed and is now found to be measured at zero are part of what makes your particular cosmic moment unique. There's no need to hold all of this in your mind. The 5 truths will keep their shape whether you remember the details or not. The Ceti program will continue regardless of whether you follow its progress. The silence will, presumably, continue to be the dominant feature of cosmic listening unless something fundamental changes. The cosmos will continue to be what it is, with all the implications that follow. What matters tonight is that you have walked carefully through one of the longest empirical results in modern science, and you have done so gently at the pace of sleep with no urgency. The cosmos is large. The silence is large. The implications are still being worked out. You are part of the generation that is alive while this is all happening. If the silence ever breaks, the breaking will be one of the most significant events in human history. If the silence never breaks, the continued silence will, over additional decades and centuries, become an even more substantial empirical result. Either outcome is informative. Either outcome will shape the cosmic understanding of future generations. We are, in this sense, alive during one of the more important sustained empirical inquiries in the history of human thought. Sleep can come whenever it wants now. The story has done its work. The cosmos that contains your sleeping body is the same cosmos that has been listened to for 60 years and has, in those 60 years, said nothing recognizable. The cosmos is what it is. You are what you are. The quiet of the cosmos and the quiet of the room are, in some sense, the same quiet. Both of them have been here long enough to deserve respect. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.